In today's lecture, I'm going to talk about the proper separation property of convex sets in Rn. So let me go ahead and give the definition of proper separation. Let omega 1 and omega 2 be two non-empty convex sets in Rn. We say that omega 1 and omega 2 can be properly separated if there exists a non-zero vector V such that Vx is always less than or equal to Vy. So here, this is the inner product of V and X is less than or equal to the inner product of V and Y for all X in omega 1 and Y in omega 2. And the second property is, and there exists X bar in omega 1 and Y bar in omega 2 such that this inequality is strict. The inner product of V and X bar is strictly less than the inner product of V and Y bar. Okay. So geometrically, this is omega 1 and this is omega 2. Then omega 1 and omega 2 can be properly separated by a hyperplane. So if we look at the hyperplane defined by V, we look at this hyperplane, then this hyperplane properly separates omega 1 and omega 2. Okay? So note that the first property, so I denote this property by 1 and this property by 2. Okay? So the first property is equivalent to supremum of the inner product of V and X, where X in omega 1 is less than or equal to the infimum of the inner product of V and Y, where Y belongs to omega 2. Okay? And the second property here can be written as follows. The infimum of the inner product of V and X, where X is in omega 1, is strictly less than the supremum of the inner product of V and Y, where Y is in omega 2. Okay? So now, if omega 1 and omega 2 satisfies the first property, we also say that omega 1 and omega 2 can be separated. Okay? And if additionally, if the second property is satisfied, then we say that omega 1 and omega 2 can be properly separated. Okay? So now I'm going to give an example in which omega 1 and omega 2 can be separated. That means they satisfy the first property but not the second one. Okay, so the example is as follows. Now let omega 1 be a line segment in Rn defined by A and B, where A is different from B. So omega 1 here is the line segment AB, and omega 2 is the line connecting A and B. Okay, so omega 2 is the line connecting A and B. Omega 2 here is equal to LAB, which is the line connecting A and B. Then we can see that the hyperplane, this hyperplane separate omega 1 and omega 2. But omega 1 and omega 2 cannot be properly separated because the second property cannot be satisfied for the set omega 1 and omega 2. Okay? And it turns out that the proper separation property is related to a very, very important concept of convex analysis called the relative interior of a convex set. And now I'm going to go ahead and talk about relative interior of convex sets in Rn. Okay, and after introducing the that concept, relative interior of convex sets, we're going to see that in order to see when two sets omega 1 and omega 2 can be properly separated, we can use the relative interior of convex sets. So now let me talk about some important concepts before introducing the relative interior of convex sets. So let's continue with the following definition. This definition is about alpha set in Rn. A subset A is called an alpha set if lambda A plus 1 minus lambda B belongs to A whenever A and B are in A and lambda is any real number. Okay. Geometrically, a set A is called an alpha set if whenever we take any 2 points A and B in A, then the line connecting A and B belongs to the set A. Okay, so whenever we take any 2 points here, the line LAB connecting A and B is a subset of this set A. Okay. So the difference between this definition and the definition of a convex set is that in the definition of the convex set, we require lambda here to be in the interval 0, 1. Okay. Over here, we require this property to be true for all lambda in R. Okay. That's why we see that A is an alpha set in Rn if whenever we take any 2 points A and B in A, the line connecting A and B again is a subset of A. Okay. Now from here we're going to see that in R3 any plane in R3, is an R phi set. Okay, because if we take any 2 points A and B in this plane and we connect them, then the line connecting A and B is a subset of A. Okay. Another example is any line in R2 is an R phi set. Okay, so this is the plane R2. Now, if we look at any line in R2, it is an R phi set, because obviously if we take any 2 points A and B in this line, then the line connecting A and B coincides with this set A, and therefore it is a subset of A. So obviously A here is an R phi set. Okay. Now, if a set omega is not necessarily an R phi set, then we can look at the smallest R phi set that contains the set omega. So that motivates the next definition. This definition is on the R phi set generated by an arbitrary set omega. Okay, the R phi set generated by a set. Okay, so the definition is as follows. Let omega be an arbitrary set in Rn. The R phi set generated by omega is the intersection of all R phi sets that contains omega. Okay, so that means, and the notation is alpha of omega. So alpha of omega, this is the R phi set generated by omega. This is the intersection of all set A such that A is an R phi set and omega is a subset of A. Okay. Similarly to the definition of convex Hall of a set, we have the following properties of the R phi set generated by an arbitrary set. So I'm going to state 2 important properties of the R phi set generated by a set in the next proposition. Let omega be an arbitrary set in Rn. Then we have the following. The R phi set generated by omega is the smallest R phi set that contains omega. Okay, so this property means that alpha of omega itself is an R phi set. Okay, and it is the smallest R phi set not contains omega, in the sense that if we have a set A, which is R phi, and A contains omega, then the R phi set generated by omega, being the smallest R phi set containing omega, is a subset of A. Okay? And the second property gives a representation of the R phi set generated by omega in terms of all R phi combinations of omega. So R of omega has the following representation. It contains R phi combinations of the form lambda I, omega I, where I runs from 1 to m. Over here, omega I, each omega I belong to the set omega. The sum of lambda I, where I runs from 1 to m, is equal to 1. And m is any integer. So the proof of this property are given in the textbook, and the proof are similar to the case of convex Hall of a set. So I'm gonna omit the proof of this proposition. Okay. So with this definition, now we are able to discuss the an important concept of convex analysis called the relative interior of a convex set. Okay, so the main idea is as follows. Now, if we look at a line segment A and B, the line segment connecting A and B in R2, as we can see, the interior of this set is empty. Okay, so omega here is the line segment connecting A and B. Okay, the interior of omega is empty because if because there is no open ball, in Rn, in R2 here, which is a subset of omega. Okay. However, we can define a new concept called the relative interior in the following way. So at first, we're gonna look at the R phi set generated by omega. That is the smallest R phi set that contains omega. So omega again is this line segment. Then the R phi set generated by omega is the line connecting A and B. So we look at A to be the R phi set generated by omega. Okay. And now, if we look at the interior of the set omega relatively to this new space, new subspace of Rn, okay, then it is the relative interior of omega. Okay, again, so if we consider A here as a metric subspace of Rn, then we can define the relative interior of omega by looking at the interior of omega relatively to this metric subspace of Rn. Then it is the relative interior of the set omega. Okay, let me formalize that definition as follows. Okay. Now, let omega be a convex set in Rn. An element x bar is said to be in the in the relative interior of omega denoted by g of omega if x bar is in the interior of omega relatively to the alpha set generated by omega. That means there exists delta greater than 0 such that the intersection of the ball centered at x bar and radius delta and the alpha set generated by omega here is a subset of omega. Okay. Now, for example, here in this situation, if we look at this point x bar, then we see that x bar here is in the relative interior of the set omega. How can we see that? At first we're gonna look at the alpha set generated by omega, which is half of omega. And now, if we look at this ball with centered at x bar and radius delta. Although the ball with centered at x bar and radius delta is not a subset of omega, but the intersection of this ball and the alpha set generated by omega it is obviously a subset of omega. So the intersection is here. So this is the intersection. Okay, this is the intersection of the ball with centered at x bar and radius delta with the alpha set generated by omega, and that ball is a subset of the set omega. So therefore, x bar here belongs to the relative interior of omega. And in fact, in this situation, we can see that the relative interior of omega is equal to the open interval connecting A and B. That means here A and B are excluded. Okay, so it contains all points of the form lambda A plus 1 minus lambda B, where lambda is strictly greater than 0 and less than 1. Okay, so the relative interior has several properties that are similar to the interior for convex sets, and at the same time we can see that for any non-empty convex set in Rn, the relative interior is always non-empty. Okay, so let me go ahead and state a very, very important theorem related to the relative interior of convex set. Now I'm going to talk about some important properties of the relative interior of convex sets in Rn. These properties are important in proving the most important theorem of this section on proper separation property. Okay, so here is the first theorem. Let omega be a non-empty convex set in Rn, then we have the following properties. The relative interior of omega is always non-empty. Okay, that is a very important property that we're gonna use later. And the second property, which is also important, so this property is similar to the property of interior we mentioned in the previous chapter. That means if we take a point A in the relative interior of omega, and then if we take any point B in the closure of omega, so A here is in the relative interior of omega, and B is in the closure of omega, then we can see that this half open interval is a subset of the relative interior of omega. So the half open interval connecting A and B is a subset of G omega. Okay, so this property can be equivalently stated as follows. If A belongs to the relative interior of omega and B belongs to the closure of omega, then lambda A plus 1 minus lambda B belongs to the relative interior of omega whenever lambda is strictly greater than 0 and strictly less than 1. And note that in the case where lambda is equal to 1, lambda A plus 1 minus lambda B is equal to A. And note that A is in the relative interior of omega, so then over here we can include 1. Okay, so I'm not gonna prove these properties. We can find the detailed proof in the textbook. Okay, so another property we're gonna use in what follows is the following theorem. If omega 1 and omega 2 are two non-empty convex sets in Rn, then the relative interior of omega 1 minus omega 2 is equal to the relative interior of omega 1 minus the relative interior of omega 2. Note that over here, the difference of omega 1 and omega 2 is defined to be the set of all elements of the form x minus y, where x is in omega 1 and y is in omega 2. Okay, so this is the set of all possible differences of elements of omega 1 and omega 2. Note that this is different from set difference. Okay, so we're going to use these properties later in order to prove a very important theorem on the proper separation. Okay, let me go ahead and state the theorem I just mentioned, the proper separation property of convex sets, and then we will try to give a detailed proof of the theorem. And because this is one of the most important theorems in convex analysis, the proof is rather involved. Okay, so let me go ahead and state the theorem. Now let omega 1 and omega 2 be two non-empty convex sets in Rn. Then omega 1 and omega 2 can be properly separated if and only if the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set. So this is a very, very nice theorem in a way that it gives not only the necessary condition for omega 1 and omega 2 to be properly separated, but also the sufficient condition. So as long as we, from this theorem, as long as we can verify that the relative interior, the intersection of the relative interior of omega 1 and the relative interior of omega 2 is the empty set, then we can say that omega 1 and omega 2 can be properly separated. And remember that the definition is as follows. Omega 1 and omega 2 can be properly separated if and only if the supremum, if there exists a vector v in Rn, and v is non-zero, such that the supremum of Vx, the inner product of V and X, where X is in omega 1, this supremum is less than or equal to the infimum of the inner product of V and Y, where Y belongs to omega 2. Okay, and also the infimum of the inner product of V and X, where X is in omega 1. This infimum is strictly less than supremum of the inner product of V and Y, where Y is in omega 2. Okay, so we already discussed this property in the previous video. So I'm gonna demonstrate this theorem in some example. Okay, so now suppose that omega 1 and omega 2 are two non-empty convex sets. Now if omega, so we have the following remark. If omega 1 and omega 2 are two non-empty convex sets in Rn, such that the intersection of omega 1 and omega 2 is empty, then omega 1 and omega 2 can be properly separated. Okay, so now if the intersection of omega 1 and omega 2 is empty, like in this situation, then because the relative interior of omega 1 is a subset of omega 1, and the relative interior of omega 2 is a subset of omega 2. So from here, you're going to see that the intersection, so from this property, we see that the intersection of the relative interior of omega 1 and the relative interior of omega 2 is also empty. And by this theorem, we see that omega 1 and omega 2 can be properly separated. Okay? So as another example, if we have a set omega and we consider a point x bar that is outside of omega. Okay? So in this situation, we can also separate x bar and omega by a hyperplane. Okay? So in order to do so, we're going to look at the first set, omega 1 here is equal to the singleton set x bar, and omega 2 is equal to omega. Okay? So in this situation, the relative interior of omega 1 is omega 1 is x bar. Okay? And therefore, we can see that the relative interior, the intersection of the relative interior of omega 1 and the relative interior of omega 2 is equal to the empty set. Therefore, you can separate x bar and omega by a hyperplane. Alternatively, we can view this as an example of the first case, because in this case, omega 1 is a singleton set and omega 2 is an arbitrary set, so that here this intersection, omega 1, the intersection of omega 1 and omega 2 is empty. Therefore, you can separate omega 1 and omega 2 by a hyperplane. Okay. The proof of this theorem, again, is rather involved, and I'm going to go through the detail of the proof by several steps. Okay. So now I'm going to discuss a very, very important property that we're going to use later on. And this property can be explained as follows. So here we have a set, a convex set omega, and we suppose that the point 0 here, the origin 0, belongs to the closure of omega, but 0 doesn't belong to the relative interior of omega. Okay? So like in this situation, we see that 0 here belongs to the closure of omega, and obviously 0 doesn't belong to the relative interior of omega. Then we can find a sequence xk, that is outside of the closure of omega, and then xk converges to 0. Okay, so then there exists a sequence xk such that xk doesn't belong to the closure of omega for all k in n, and xk converges to 0 as k converges to infinity. Okay? Okay? So let me go ahead and formalize the theorem and give the proof. So this is lemma 1. Lemma 1. Let omega be a non-empty convex set in Rn such that 0 belongs to the closure of omega, but 0 doesn't belong to the relative interior of omega. Then there exists a sequence xk in Rn such that xk doesn't belong to the closure of omega bar for all k, and xk converges to 0. Okay. So the statement looks complicated, but then if we demonstrate this lemma by a figure, we're going to see that the proof is very, very simple based on properties of the relative interior for convex sets. Okay, so the main idea is as follows. Now let's look at this figure. Because omega is a non-empty convex set, its relative interior is non-empty. So we can find a point x0 that is in the relative interior of omega. Okay, and so here is the point x0. Okay, and then we look at all vectors of the form t minus t x0, where t is strictly greater than 0. So from this figure, we're going to see that minus t x0 doesn't belong to the closure of omega, and therefore, if we pick t to be 1 over k, so that the sequence xk here is equal to minus 1 over k x0. Then this sequence satisfies the required property. Okay, so let me go ahead and give the detailed proof. Since omega is non-empty, there exists a point x0 that is in the relative interior of omega. Then minus t x0 doesn't belong to the closure of omega for all t greater than 0. Let me go ahead and prove this claim, although it is apparently clear from the figure. So by contradiction, indeed. So by contradiction, suppose that minus t x0 belongs to the closure of omega for some t greater than 0, then we have the following representation. Now if we look at 1 over 1 plus t times minus t x0, and over here we look at t over 1 plus t times x0. Okay, so because here we suppose that minus t x0 here, it is an element of the closure of omega, and x0 here is taken in the relative interior of omega. Okay, And the sum of t over 1 plus t and 1 over 1 plus t here is equal to 1. Okay, so we put this one by, if we put this one by lambda, then this one will be 1 minus lambda. Okay, and this sum is obviously 0 because the top here is tx naught and this is minus tx naught, and the denominator here is 1 plus t. Okay, so this sum is equal to 0. Okay, and at the same time, we already stated a theorem earlier saying that if we take a point x naught in the relative interior of omega, and if we take a point b that is in the closure of omega, then any point in this open interval is in the relative interior of omega. Okay, so this half open interval is in the relative interior of omega. So that means here the point 0 being lambda times x naught plus 1 minus lambda times minus tx naught, and this is an element of the relative interior of omega, and this is an element of the closure of omega, and lambda here belongs to the open interval 0, 1. Therefore 0 belongs to relative interior of omega, which is a contradiction. Okay, because by the assumption 0 doesn't belong to the relative interior of omega. Okay, so now we have proved that minus tx naught doesn't belongs to the closure of omega for any t greater than 0. So now let xk be minus 1 over k times x naught. Then obviously xk doesn't belong to the closure of omega for all k, and also xk converges to 0 as k goes to infinity. Okay, so we have completed the proof of this important lemma.